Hello and welcome to the part 2 of Sudoku, Magic Square and SudoMagic. In part 1 we have started with Ramanujan's Magic Square and we have explained what they are and what are the interrelations among them, why they are interesting and moreover why they are challenging. And in part 2 today we will be discussing solving the AIs by solving the problems by AI, artificial intelligence method. Okay. A quick comparative summary of the hardness level of these three problems. Suppose we have taken n by n grid or matrix. So the number of numbers is n square, and that n square number can be either 1 through n square or n set of 1 through n. For 9, it should be 1 to 9 square, that is 81, or n sets of, that means 9 sets of 1 through 9. So how many rows and columns? 2n, n rows and n columns that are common to all three problems. And then for three different problems, some extra features are being added. 2 diagonals for Magic Square, 9 inner blocks for Sudoku, and if combined, then 2 diagonals and 9 blocks for Magic Sudoku. So another point that for Magic Square, you can use any n, 4, 5, 6, 7, whatever it is. But for Sudoku and Magic Sudoku, it has to be a square number, n, 4, 9, 16, etc. And the total number of constraints, if you call it so, then it is 2n, that is the common, 2n plus 2, 2 diagonals, 2n plus n, n blocks, and 2n plus n plus 2, n blocks and 2 diagonals. So obviously, it is constant. Magic Square is highly constant, but Sudoku is more constant, and Magic Sudoku is the most constant problem. Well, a quick look that we have also presented in the first part. Magic Square, not a Sudoku. As you see, the sum of the numbers along the row, column, and diagonal are same, and that is the magic sum 45 for this case. But the inner blocks, if you add this 3 by 3 or this 3 by 3 or this 3 by 3, then you will see that 9 such inner blocks, their sum is not 45, rather they are listed here, all are different. And here it's a Sudoku but not a Magic Square. So here you see the sum, row, column and inner block are same, 45, but the diagonals are not the same. And that is quite obvious. If you look at the Magic Square, then you see that all the numbers 1 through 9 are there in both the diagonals. So the magic sum is 40. But here some repetition, 1 is there. So naturally the sum is not 45, rather 40 and 30. And now the hardest one, the sum for row, column, inner blocks and diagonals. All are same and equal. So this is the example. You can give a pause and you can check whether all are same or not. Well, in today's time, most of the magazines and daily papers even, they supply some Sudoku problems, and there are many people who enjoy to solve the Sudoku problem daily. But unfortunately, they don't handle with Magic Square or SudoMagic. Obviously, they are more difficult problems. Say, for example, I have taken one from the Telegraph. They call it diabolical, the most toughest one. And the AI solution is this. Okay, one can solve this manually, but my AI solution is this. And remember that the red letter numbers, they are actually the same red letter numbers. That means the corresponding position of those red numbers are kept as such intact. That is given by the problem, so you cannot touch them. And I have filled up the rest of the spaces, vacant spaces. Okay. Now it's time solving by AI. So as you know that learning is critical to all AI methods. So the area is often referred to as machine learning. And a few examples, there are so many actually. Expert systems, neural network, genetic algorithm, and so on. And the learning strategies like expert systems may use any of the existing methods to learn, but ANN and genetic algorithm usually learn by inspecting examples or by investigating the environment. But today we'll be exploring not these methods but simulated annealing method SAM, and which learns or decides by Boltzmann machine that I will explain in a while. So why SudoMagic is a challenging problem? Initially, it's a constraint optimization problem, and not only that, it's NP complete class of computational, as we have explained in the first part, and it's an ideal test bed for algorithm development and benchmark study for a computational intelligent algorithm. And why simulated annealing? Okay, if you go for the exhaustive search tree-based methods, it is clearly a combinatorial explosion problem, so it would be very difficult. But by AI method, it would be much easier. And because SAM was at our disposal, so just we could have used any other method as well. And just an outline of SAM, it actually replicates or mimics a very natural process, which is cooling of high temperature liquid. How? If you compare with your computational algorithm, this cooling method of real liquid, the energy of the liquid is compared to some objective function or functional of the problem. And if you cool the liquid slowly, you are sure to reach the perfect crystal. But if you cool it faster, then probably will reach a metastable crystal. So in parallel, if you anneal the functional, anneal means you are as if decreasing the temperature by changing, of course, the variables of the function, and then by applying some suitable Boltzmann machine that I will explain in a while. But if you are fast enough in your cooling or annealing, you will reach a local minimum like metastable crystal. And if you are slow enough, then you are certain and sure to reach the global minimum, that is the perfect crystal. Okay. So as you see, it's a highly constrained optimization problem, an optimization of some functional that you have defined according to your problem, very selective. Now the question, how to define this functional f? Of course, in such a way that minimum of that functional will correspond to the solution of the problem, right? As simple as that. So in our case, I will explain why that this functional f is nothing but variance v. And what is variance? Suppose a set of values x, x1, x2, dot 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 xn. Then variance is the square average of those values minus average square of those values. Okay, and it can be shown that in this way v is greater than or equal to 0, and physically what it signifies, that is, it represents spread of x, distribution of x values around the mean x value, right? Now an interesting situation arises. If all the x1 to xn all are same, then the average would also be the same value. That means that no deviation, the distribution is just a perfect straight line, no spread, so v should be 0. And in your problem, if you define v in such a way that minimum of that v, that is 0, corresponds to the solution. So that is how I have not yet explained. But before that, let me quickly see that my demand is true, that when all the values are same, what happens? Suppose you have taken all different values, 1, 2, 3, 4, 5, then the x average is nothing but 3 and square of it is 9. But if you take the square average, then you square the terms, then you add, and you will get the average to be 13. So if you calculate the 13 minus 9, and that would give you v not equal to 0. Not equal to 0. But now you take all the same values for x, all a. So x average is just sum of this 5a, that is 5a by 5 is a, and square of it is a square. But x square average, first you square and then you add to get 5a square by 5, and that again gives you a square. So this time a square and a square, obviously v is 0. Clear? Okay. Now the main question, how I define my variance. So variance is perfectly suitable functional for our problem. I have demanded. Okay. Now variation of what? What values? X values, variation of a set of x, right? But the question, what are those x? Of course, if V is 0, that must correspond to solution. And at that solution, you want some of the x values or set of x values are set. Now the most important question. At solution, what set of values we want to be the same? What values? And now anyone can answer according to the problem. Of course, they are the constants on magic sums. Is I means 1 to 2n or 1 to 2n plus 2, 1 to 3n plus 2, etc. That means row, column, diagonals, etc. The sum of all the numbers along those rows, columns, and diagonals must be same. So they are constants, and the constants must be same. How many constants? As I mentioned, it's different for different problems. Okay. For example, if n is 9, then it is 20, 27, and 29. Okay. So precisely in our problem, variance is s square average minus s average square, and you have to calculate s square average, the sum over square of si by 3n plus 2, and similarly s average. And why 3n plus 2 is obvious. I am handling the magic Sudoku, that is 3n plus 2. So how many constants? 3n plus 2. So you have to divide it by 3n. Okay. And for example, I have taken an arbitrarily randomly chosen numbers 1 through 25 to give a 5 by 5 square. But here, as you see, the sum of the numbers along the diagonal, along the column, along the rows are not same and not equal to 5. I mean, no, for 5 it should be 65. Well, but here, after some rearrangement, proper rearrangement, all those numbers 1 through 25 are arranged in such a way that the sum of the numbers down the column, along the row, and along the diagonal are same, and that is equal to the magic sum 65 for 5 by 5. Okay. But interestingly, if you calculate just by using a calculator, you will see that in the first case, all the numbers are different SI values, so variance is not 0. But in the second case, all SI values are same, supposed to be same, so V is supposed to be same. Okay? And you can check. Well, the method of simulated annealing, just to outline. So initially what we do, we call it a matrix, the grid or matrix 9 by 9 say, and we initialize the matrix by taking random numbers 1 through n square or 9 sets of 9. Okay. Then second step is to evaluate the sum of the numbers along the row, column, and diagonals, and then you calculate the square average and average square, and you calculate the variance. Okay. And then the most important step, the annealing step. You repeat for steps in T. That means for a particular temperature you have taken, and how many steps that you have declared as input, that how many steps it will search. Search means what it will do. It will swap between a pair taken randomly the values of those two elements or pair of elements. And then obviously the variance value will change. You calculate that new variance. Now 2 steps to follow. Whether you will accept this change or exchange. Number 1 case, if the new value is less than the old one, then you accept because you want to minimize the variance. But if it is not so, that means if V new is greater than V old, then also you are not downrightly rejecting the step. Then you calculate some probability, which is Boltzmann probability, e to the power minus delta V by T. Delta V is the difference between these two. Okay, new minus old. So it gives you a probability. So is it probable? If it is greater than some random number 0 to 1 generated at this point, then you accept. So 2 cases arise. But if in both the cases it fell, then you reject the exchange. You stick to the older. Okay. So this is actually what we call the Boltzmann machine decision, because you are using some Boltzmann probability factor. Okay. Now after step 3 in step 4, you reduce the temperature now by some fraction pi t, and you do the third step again. For how many steps you will be doing? Now this is steps of. It was steps in T. Now it is steps of. That means how many temperature steps you have declared as your goal. And what is the stopping criteria? If V is 0, then you stop, or the number of steps, temperature steps are exhausted, then you stop. Okay, and then you may increase in the next run the number of intervals to higher, or you can play with the parameters. So what are the parameters? T for temperature, Tfac in my program, Tfac is the 5, steps in T is NT, and steps of T is Ntemp. So these are the input parameters in my program. Of course, I'm not showing the program, it will be boring. Now, it's a typical annealing profile. I'm minimizing variance, so it starts from a very high value and it go ups and downs, and finally converging to give a 0. Okay. Now, these ups and downs are quite meaningful here. These are called the local minimum, and here it reaches the global one. But you are allowing, since the Boltzmann machine decides over the probability factor, so sometimes it is probable that you can go jump off at the local minimum and to some different configuration, and then again you can have the possibility to reach another local, and so on. Finally, you are reaching the global solution. Well, now let me show some of the interesting observations of this program. First of all, are there more than one solutions? Of course, it would be a bad problem if there are more than one solutions for a single problem, right? But the question is, can this method find multiple solutions? If they are there, the answer is yes. How we can do that? Very simple. We just start in different run with different starting configuration. Now, what does it mean? That you have to start with randomly taken numbers in the vacant positions. Of course, you cannot touch the elements provided by the given Sudoku. So if the starting configurations are different, then possibility is there that you can reach another solution if it is there. Okay. So let us see a quick example. I have taken it from a very famous reference given here, and they call it extremely difficult problem as Sudoku, and they have provided the solution as well. So I took this as the input to my problem, and very interestingly, I found that there are at least 3 solutions. Solution 1, solution 2, solution 3. You can notice that the bold letters are the same in the corresponding position as was given in the problem itself. So that is an interesting observation, that it can find more than one solution. Now, second question, that Sudoku, Magic Square, and SudoMagic, all 3 are different problems. But can all these 3 be created from the same input? Of course, it is randomly taken or randomly maintained and read by the same program. So the question is whether your program is a very general one, so that you can change the option as you wish to get Sudoku or Magic Square or SudoMagic. Again, the answer is yes. All 3 can be created. Here, for example, initially I have taken 1 to 81, the 9 by 9 case, numbers 1 to 81, but random. So naturally, we don't expect the sum of the numbers along the row, column, or diagonal to be the same. And 369 is the magic sum we know for 9 by 9 problem. You see, all are very different, right? Row, column, and diagonal. So it's quite expected. But now you run your program with this input, and you see you have given option for magic square. So you see that for rows and columns and 2 diagonals are all the same. But if you check, then you will see that the inner blocks, their sum is not 360. So it's not a Sudoku. And then the same input, so it's a magic square, but not a Sudoku. Okay. Then with the same input, we now give the option for Sudoku. Then you see the row, column, and blocks are same, sum of the numbers, but not the diagonals. If you check, you will see not the diagonals. So it's a Sudoku, but not magic square. And here, the toughest one, you give option for Magic Sudoku or Sudoku Magic. Then you will see that all the blocks, diagonals, rows, and columns, their corresponding S value, sum value, same and is equal to P16. Well, here we have used the option 1 through n square, but the most popular one is, the conventional one is 1 through 9, 9 such sets. So again, 81 number of numbers. So I have tried that also, the same motto, that from the same puzzle whether we can create all three problems, Magic Square, SudoMagic and Sudoku. Yes, this is the trial puzzle we have taken. The same input I have given for this tree run with three different options. So it gives you the Magic Square, it gives you the Sudoku, and it gives you the SudoMagic. You can give pause to look at the solution and check my demand whether they are true or not. Okay. So that is all about our part 2 on this series of Sudoku, Magic Square and Magic Sudoku. And now it's time to thank you. Sudo magical thanks for watching. Thank you very much.